All right, so for the first part of lecture B, we're going to do a careful proof that this integral converges. Actually, we're interested in the integral from 0 to infinity. But again, like I said, the integral from 0 to 1 is trivial, okay, because it's not improper. So I'm going to focus on the integral from 1 to infinity to keep our proof a little shorter. If I put this on a test, what should you do? Could I put this on the test? Possibly. Okay, you should be able to handle something like this in the following kind of way. You have to do a little scratch work, essentially, with what I erased, to try to figure out what function to compare it to, or maybe I can tell you, give you some guidance. Our f of t is this function. The g of t that we sort of figured out with a little bit of scratch work is 3 over t squared. You want after you do the scratch work, or maybe after I tell you what to compare it to, you want to put those things in here in the first sentence. Let f of t equal 2 plus sine t over t squared plus 1, and g of t be equal to 3 over t squared. You'd want to define those first, either based on scratch work to try to, because you figured out that this function is always below that one, or to save you some stress, maybe I'd tell you what function to compare it to. What should you say next? You should say, since 2 plus sine t, let's focus on this thing first being non-negative, is greater than or equal to 2 minus 1, or 1, which is greater than 0, and t squared plus 1 is greater than 0 for all t, it follows that f of t is bigger than 0 for all t. In the theorem, the comparison test theorem, you only need greater than or equal to. But our function is actually strictly greater. It doesn't really matter if I put a greater than a less than or less than or equal to right there. By the way, I hope you know it's okay to also write this as f of t greater than 0. Those mean the same thing. Also, since 2 plus sine t is less than or equal to 2 plus 1, which is 3 for all t, it follows that f of t is less than or equal to g of t. Oh, what? Excuse me. I need to add more in there, sorry. And t squared plus 1 is less than t squared for all t. It follows, greater, sorry. It follows that f of t is less than or equal to g of t for all t. I know this is kind of long-winded, but I'm trying to get every detail in there. Why does that follow? Well, the numerator of f is less than or equal to the numerator of g. And the denominator of f is greater than or equal to the denominator of g. If you divide by a bigger number, you get a smaller number. So in both ways, in both respects, the fact that this numerator is less than that one, and this denominator is greater than that one, this fraction is going to be bigger than that fraction for all t. You've got a bigger number up top there, and a bigger number, excuse me, a smaller number up top, and a bigger number at the bottom for any fixed t than this. So this has got to be greater than that. Almost done. We know, because it's in the book, and I'm telling you, you can say we know this, that the improper integral of g of t from 1 to infinity converges. It's a constant multiple of 1 over x to the p, where p is greater than 1. P is 2. Remember that example? Integrating 1 over x to the p. From 1 to infinity, the integral converged when p was greater than 1. P is 2 here, bigger than 1. The 3 up there was a 1 before, but it's just a constant. It doesn't affect the convergence. You can definitely say, we know this integral converges. Biggest place where people make mistakes here is they forget to put the integral sign there. I see it all the time, and even when I'm warning you to make sure you put it there. The issue is not whether g of t converges or not, it's whether this improper integral converges. And you know it does converge. Make sure you put the integral sign there. And make sure you put the integral sign in what I'm about to write next. Therefore, and you can use 3 dots for therefore, the improper integral we're interested in also converges. Make sure you put the integral sign there. And that does it. There's a real formal proof using the comparison test that the improper integral we're interested in does converge. When you finish a proof, commonly mathematicians start talking in Latin and putting QED, quadrat demonstrandum, meaning I'm done. Or Christian mathematicians often put PTL, praise the Lord. Either way is okay. Question?
If g of t diverged, then it would prove nothing about f of t.
Right, if the integral, say the integral, if the integral of g of t diverged and this was still true, it would say nothing about the convergence or divergence of the integral of f, yeah. Although if the inequality was switched to a greater than there, then it would say the integral of f diverges as well. The integral of g out to infinity is a finite area. It gives you a finite area for the region going out to infinity under the graph. The graph of f is underneath it. So it's got to have a finite area out to infinity as well. Is the intuition behind what we do. Feels kind of stuffy, feels kind of constraining to write things in this way. Tiresome, unpleasant. What I want you to understand, the way you structure a proof is a logical manner. You need to clarify that you need to verify that the hypotheses of the comparison test hold. Hypotheses being related to this one and this one, those inequalities, and the fact that you know this converges leads you to the conclusion that that integral converges. Again, the biggest mistake people make is forgetting to put the integral sign at the end there in both spots. It is necessary. All right, so we've got now about 22 minutes to do volumes of revolution. We're still going to do volumes by slicing. Your hand is a knife. Actually, I said this in the second class yesterday, but I didn't say it with you guys. Anybody like watching The Flash? Anybody? TV show, one person? Okay. And there's going to be like a Flash in the movies too. There's a new Justice League movie coming out or something. Anyway, in the Flash TV show, this might happen in the movie. The Flash and other speed people, they're like shaking their hands really fast to like try to kill each other. I mean, the Flash doesn't try to kill people that way because he's a great guy, but the evil speed guy shakes his hands like at the speed of light almost and sticks it in people's chest to stop their heart. So it made me think of that as I was doing this kind of thing, slicing up the solid. You pretend your hand is a knife and you're slicing the solid that you're going to find the volume of. But what is a solid revolution? You got to take a region in the plane and rotate it around an axis to create a solid revolution. Let's start simple. Let's say our region that we're going to rotate around an axis, and it's going to be the x-axis, is the region under the graph of y equals x squared, x going from 0 to 2. So this region right here is going to be the region that we rotate around the x-axis to create a solid. When you try to draw these things, people typically run into trouble, me included. They get difficult to draw sometimes. You have to use your imagination. You're rotating this around the axis, so now you need to think three-dimensionally. There's like a z-axis coming out of the board at you. What kind of solid will you get? It'll be kind of like a cone, but with curved sides on its side. Maybe it'd be better to call that a horn. How's that for a first approximation? It's even tougher to draw on a board. Oh, I'd probably put the left side of this disc shape a little closer, but not too bad. Can you imagine it? It's like a horn. Put your mouth over here. Except there is really no opening, though. It's a horn with no opening. What is its volume? That's what we're after. Get your knife out, slice, 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 at some value of x. I'm going to mark some value of x here. Now realize that this x is just a label for the axis, whereas this x represents some particular value along the axis between 0 and 2. Are you okay with two x's with two slightly different meanings here? You slice it, what's it going to look like? You're slicing these things again super thin. How thin? Infinitesimally thin. Thinner than an atom, thinner than an electron, thinner than a quark, if you've ever heard of quarks. Thinner than a string from string theory. Basically no thickness at all, though you imagine it's got a tiny thickness. An infinitesimal thickness. Now, there is no such kind of thickness in the real number system, the standard real number system. Turns out there's a non-standard real number system where there are such things, but we don't learn about that because it's just way too hard. What do you call this infinitesimal thickness, which I will draw with a certain amount of thickness to it? Call it dx. This is not the book's approach, by the way. The book calls it delta x for one thing, though delta is the Greek version of d. And they think in terms of Riemann sums to approximate the volume. And that's all good and fine. In the limit, it tends to an integral. But that's not typically what your physics professors, chemistry professors, and other kinds of people do. It's not typically how they think. They do realize that when you want to approximate integrals, sometimes you have to do summations. Simpson's rule, ultimately. But they kind of just want to get to the answer as fast as possible and think intuitively about it. So it's a really, really, really thin hockey puck, so to speak. Really thin hockey puck. Wafer might be a better thing to call it. The cross section, when you look at it head on, like from this direction, looking at it head on, is a disk, a circle on the inside of a circle. That's supposed to be a circle there. A of x is the area of that cross-section. It's the cross-sectional area at that value of x. And it gets bigger as x gets bigger. What's the area of a circle? Pi r squared. Yeah. Where r is the radius. R, the radius of the circle, the disk, depends on x. As x gets bigger, you move to the right, the disk gets bigger. This disk is smaller than this disk. A depends on x, but so does the radius in this case. That depends on x. What is the radius? Look back at this picture. For any given x, the radius is the distance between the x-axis the axis that you're revolving around, and that graph, y equals x squared. That'll be the radius. The original function, f of x, is really the radius. That's the same as r of x. So for this example, this becomes pi times x squared squared, pi times x to the 4th. And that'll be the function you integrate. But wait, before we write down the integral, let's think intuitively about how to derive the integral. So come back to the hockey, the really thin hockey puck, thin wafer here. Its width, its infinitesimal width is dx. What's its infinitesimal volume? What's dv? It would be the cross-sectional area times its infinitesimal width. It would be a of x dx. So to find the volume again, now you think intuitively of the integral sign as adding. To find the total volume, b, add up the little volumes, the dv's. This is your conceptual equation. Conceptual equation. It's not telling you what to do to find the answer. It's giving you the intuitive idea of the volume as a sum of little volumes. Pretending the integral sign is a summation. Technically, it's not. And that's not a summation for us. It's a limit of summations. It's a limit of Riemann sums, technically speaking. But that's sort of like almost a sum. So why don't we go ahead and pretend it's a summation? Add up the little volumes to get the total volume. But what is dv? dv is this. You're ultimately integrating a of x. And what is a of x? And ultimately you want a definite integral. A of x in this example is pi times x to the 4th. X goes from 0 to 2, so we integrate this from 0 to 2. Giving pi x to the 5th over 5. And the answer is going to be then 2 to the 5th pi over 5, which is 32 pi over 5. That's the volume. Numerical value. What would its units be? Its units would be cubic units of length. So if x and y were in inches, that would be cubic inches. If x and y were in meters, it would be cubic meters. Let's do a trickier one. One way this can get trickier is if your region that you're rotating is not, well, one of the sides is not the x-axis, for example. The top and the bottom are two different functions. Another way it gets trickier is if you decide to rotate it around some other axis. Say horizontal still, some other line, like maybe y equals -2 instead of y equals 0, the x-axis. So this time, let's take the region between the graphs of y equals x squared and y equals square root of x from 0 to 1, and not rotate it around the x-axis. Let's rotate it around some other horizontal line, like down at y equals -2. Find the volume of the solid that results. What will that solid look like? It's even harder to draw. That distance right there is 3, so this is technically, I've got to go down to like -5 down here. Definitely not a perfect drawing. I'm kind of too far out of room down here at the bottom. Let's see. It's dangerous to try to draw these things. Kind of like that, except I go down further. You also need to realize that it's hollow in the middle because you've got this space. The space between the part up here and the part down there is not part of the solid. It's more like a bowl with a hole on its side. And if you grab the bowl like this, it would feel thicker in the middle than in the top or the bottom. Imagine taking this and putting it on a table. It would look like a bowl from far away, except it would have a hole in the bottom as well as a hole in the top. And if you put your fingers around the bowl, it would feel thicker in the middle, like when x is close to a half here, than it would when x is close to 1 or 0, where it would feel thin. That's the solid we're trying to find the volume. You do it by slicing still. Get your knife out, slice. Where? At some value of x. Giving you a cross section. My markers are starting to fail me here. And it's getting tough to tell what I'm drawing. If you look at that in the right way, you realize it's like a thin ring. The cross section, when you look at it head on, is like a thin ring. Head on, it looks like that. This marker's getting worthless here. Head on, it looks like this. And it's got a little infinitesimal thickness to it, dx. Zoom in on these things to see that. dv, the volume of this infinitesimally thin object, is still a of x dx. So you still integrate a of x. What's the cross-sectional area of this thing? It's a ring, and it's an annulus. It's a washer, people say. You know, washer like with screws. Put it on a screw to get it tight. That kind of washer. Different names: washer, annulus, ring. Any of those three words is fine to use. What is the cross-sectional area? It's the area between two circles. Take the area of the bigger circle minus the area of the smaller circle. It's got an inner radius, r in, and an outer radius, r out. It's supposed to be an out here. A of x is going to be pi times r out of x squared minus pi times r in of x squared. You can also factor the pi out and write it as pi times, in parentheses, r out of x squared minus r in of x squared. And then when you do the integral, the pi can just be in front of the integral sign. So the volume of the solid is going to be pi times the integral from 0 to 1. How do you find the inner and outer radius? Radii? You got to look at the picture and think carefully here. The axis of rotation is y equals -2 down here. The distance between that line, the vertical distance, and the lower graph is r in. And the distance between that line and the upper graph is r out. Yeah, these markers. Zoom in if you need to see that more clearly. So that distance right there, that's r in. This distance right there, that's r out. Depend on x, depend on these functions. but they're not equal to those functions, R out is going to be square root of x is this distance from here to here plus 2. That gets squared, and R in is not x squared because that's that distance, but x squared plus 2 because that axis is down at -2. And this is definitely doable. Let's go ahead and do it. Multiply things out. FOIL. Square root of x times itself is x. Outside times outside and inside times inside is going to give you 4 square root of x, which I'll write like this. 2 squared is 4. Minus x squared squared is x to the 4th. Foiling, thinking about the outside and inside, I'm going to get minus 4x squared and then a minus 4. The 4's do cancel. Integrate what's left over. Don't forget the pi. 1/2 x squared for the first one. X to the 3/2 divided by 3/2. When you divide by 3/2, it's the same as multiplying by 2/3. 4 times 2/3 is 8/3. Minus 1/5 x to the 5th minus 4/3 x cubed from 0 to 1. Pi times 1/2 plus 8/3 minus 1/5 minus 4/3. Common denominator would be 30. 8/3 minus 4/3 is 4/3. Pi times 15 over 30 is the 1/2. 4/3 over 30, that's going to be plus 40. And then the 1/5, there's something over 30, it's going to be 6 over 30 minus sign. 49 pi over 30 would be the volume. Okay. Does it look right to people? See any mistakes at all? Let's just check it with Mathematica, then we'll be done. I can do it R in. I'll use capital R. That's not rin, that's R in. R in of x was x squared plus 2. R out of x was square root of x plus 2. I want to do pi times the integral from 0 to 1 of R in, or R out, squared minus R in squared 49 pi over 30. Okay? So, again, we'll just take 30 seconds to summarize. The final answer, you know, if your integral is not too hard to calculate, is not too hard to calculate, you can use the formula. Understanding where the formula comes from, that's the harder part. Okay? So, I mean, you do need to use some problem solving and some visualization to understand geometrically what's going on with the revolution. But really work on this scientist kind of approach to things. We will do Riemann sums again eventually, but we're sticking with the scientist approach to things right now. All right, see you on Friday.